Hello, welcome to Pipeline Integrity, Depth Correction Factors to Account for Stress Corrosion Cracking Shielding Effects. I'm your presenter. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, up in Canada. For those of you that have seen some of my previous videos, I think I should let you know that this video is a little bit more advanced than some of the others. You're going to have some pretty good knowledge of fracture mechanics to follow some of this, so just a bit of a heads up there. Today I'm going to be talking about stress intensity shielding in stress corrosion cracking colonies. Most of the time when we're doing pipeline integrity work and we're looking at SCC cracks, typically the assessments are done just assuming that there's one single crack. But actually most of the time when we look at SCC, the cracks form in colonies, which means that we've got multiple parallel cracks that are all kind of lined up nice and neatly next to each other. Now what that actually does is it produces a shielding effect where the stress intensity factor is not focused on one individual crack, but it's actually spread out over several cracks within the colony. What that means is that our stress intensity factor is actually a little bit less than we think it is. And that makes a difference when it comes to the assessment calculations. So what I'm doing here is I'm taking a look at the stress intensity factor solutions that are available in industry, and I'm demonstrating that they can be used to come up with a correction factor for your fracture models that gives you pretty good predictive capabilities at what sort of pressures the SCC colonies can fail. I'm going to be relying on several important industry references, some of which will be very familiar to some of you and some of which not so much. I'll be looking at Tada, Paris, and Irwin, their classic textbook, The Stress Intensity Analysis of Cracks Handbook. So anybody in the fracture business will be, I think, familiar with that one. That one is a gold mine of great information. I'll also be looking at a paper which is probably not known to most of you. It was written by Parker in 1999, and it's called Stability of Arrays of Multiple Edge Cracks. I found it in my local university library. You guys probably can too, though it will take a little bit of digging around. I strongly recommend that paper for anybody that's involved in stress corrosion cracking. It's not an easy read, but I found it really a fascinating piece of work. I'll be looking at the Pipeline Research Committee of the American Gas Association's 5th Symposium on Line Pipe Research Notes from November of 1974. I'll be mentioning some work by Rothwell and Coote, the Critical Review Assessment Methods for Axial Planar Flaws, which was a pipeline conference in 2009, and then more recently a PPIM conference in February of 2020, Davies, Slater, Post-Alexander, and Denow, burst testing of pipes containing stress corrosion cracks. So as I go through this presentation, I'll be referring back and forth to these references. Now, if we go to Tada, Paris, and Irwin, and we dig around, we'll actually find that they came up with a stress intensity factor solution for periodic crack arrays. And so here I've copy-pasted out a couple of the key things. Here's a geometry on the right where they show you they've got a periodic crack array where the cracks are all of depth A. And then they've come up with a spacing parameter between each crack that's equal to 2h. It's a little bit confusing why they would do that, but it comes down to the mathematics that they were playing with, and they found a certain convenience in doing things that way. Now they defined a spacing parameter S, which is equal to A, the crack depth, divided by A plus H. So the crack depth plus the half spacing between cracks. And they play around with the math a little bit on that. It's a bit tricky to wrap your head around, but as we go through, I'll try and give you a few pointers to hopefully help you get your head in the game. Now, if you look at their work, they've actually come up with two different ways to do the stress intensity factor calculation. The first one, which I've highlighted in pink, is they just take the standard stress intensity. They have a compliance factor, which I'll call F1 here, and then they've got the usual stress times the square root of pi times the crack depth. But then they also come up with a slightly different way to do things. And here I've highlighted another equation in green, where they have a stress intensity factor solution, which is equal to a compliance factor 2. And rather than having stress and pi, square root of pi times the crack depth, they have stress times the square root of h. And it might not be immediately obvious why they do that, but hopefully as we look at the next plots, it should become apparent what they're trying to do. So here we have a plot that's straight out of the Tada work. On the y-axis, we have the compliance factor. And at the x-axis, we have this S factor that Tada has defined. And so when we go from left to right along the plot, that represents crack growth. Now, first we'll look at the red curve. That's your standard stress intensity factor compliance solution. You'll see it goes from the top left of the plot to the bottom right. At the top left, you'll see it intercepts at 1.12. And so if you're familiar with fracture mechanics, you'll know that that corresponds to your classic edge crack solution. Now you'll see that as the crack grows, as we go from left to right, that red curve actually goes down. That means our compliance factor is going down. It doesn't mean our stress intensity factor is going down. And we have to think that our compliance factor goes down at the same time that our crack depth goes up, and so we've got essentially two competing parameters to think about. And that's not necessarily easy to rationalize in your head what's going on, and that's why Tada and the others came up with the green line. So that's where they've got compliance factor 2. And what's interesting there is you start off in the lower left portion of the plot. The stress intensity factor, compliance factor, actually goes up, and it peaks right around S of 0.4. And after it peaks at that point, it actually goes down a little bit, which is a very strange thing to think about. Now, when you look at the stress intensity factor of the green line, you can consider that the H value is not changing. Your cracks are not getting closer or farther apart from each other. They're just they're maintaining a constant, and therefore that green line actually represents what the classic stress intensity factor would be doing as the crack grows. Now I highlight these areas a little bit that are really key sections. When your green curve peaks at S equals 0.4, our red curve, if you drop down, our red curve is lower down. We have a different compliance factor to use for our classic solution. So if we were working with the green curve, we would be looking at a compliance factor of 1.03. But if we want to translate everything into our standard red curve, then we've got a compliance factor of 0.72. A little bit tricky to wrap your head around, but we'll just have to sort of plow on. Now, Parker in 1999 wrote a very, very interesting paper. And what he did is he demonstrated that when that S ratio equals 0.4, that's the equivalent to A over 2H, so a crack depth divided by crack spacing ratio of 1/3. It's exactly 1/3. And he said, because we've got a peak in our green curve, the cracks have actually become thermodynamically sort of metastable. If they grow any deeper, the stress intensity factor will go down, and that's not thermodynamically reasonable. And obviously, the cracks can't heal themselves and go the other way down the curve. So what ends up happening is they become metastable. Now, Parker made the argument that the array can then experience something he calls crack shedding. And what happens in that is 2/3 of all the cracks will shed. They'll, for all intents and purposes, they'll go dormant. And then 1/3 of all the cracks will continue to propagate. But they'll continue to propagate with a new spacing ratio, A over 2H equal to 1/9. Right? And then what will happen is those cracks will propagate until they reach a spacing ratio of 1/3, and then they will shed again. And they'll go through a crack and shed sequence potentially several times as long as the stress is acting on those cracks and there's sufficient stress intensity to drive the cracks. Now, Parker's demonstrated that this particular sequence occurs in mud cracking, permafrost cracking, cooling of basalt columns, and he also demonstrated it in gun tubes. Now, when you go through the logic of the cracking and shedding sequence, Parker's going to predict a fairly regular pattern in the depths of cracks, and that pattern is going to be based on the spacing ratio. So if you look at these, it kind of looks like you're looking at a ruler, but rather than looking at inches and half inches and quarter inches, you've got this 3-to-1 spacing ratio. Now, obviously theory is nice, but does it work for real? Well, Parker demonstrated it in cracking in a gun tube. So if you look at this photograph, on the right and the left, you've got very deep cracks, and then equally spaced in the middle of those two cracks at about the 1/3 of the way along and 2/3 of the way along, you've got these medium cracks, and then within those areas, you've got really tiny micro cracks. It's not a perfect representation of what we just saw in terms of the pattern, but you can tell that there is a 3-to-1 spacing and a ratio in the deeper flaws to the medium flaws to the shorter flaws that's about 3-to-1. So that I think that provides some pretty reasonable evidence that Parker was onto something. Now, let's take a look at the math here. if S is equal to 0.4, then we can go through the operation and say that our depth to spacing ratio A over 2H will equal 1/3. And then if we then go through some shedding, we'll have an A over 2H ratio of 1/9. And at that point, working backwards, S becomes 0.18. So we can then go to our curve and we can ask ourselves, what are the compliance factors at a S value of 0.18? And it turns out that that those values of 1.03 and 0.72 that we saw before are actually mirrored, but on the opposite curves. So that's kind of an interesting coincidence. And what it means is that as our cracks are going through their crack and shed sequence, they're alternately going to bounce between factors of 0.72 and 1.03 as their compliance factors, provided that they've done that first round of shedding. Now, it seems to me that Parker's work was very, very interesting in that he demonstrated in all sorts of different natural phenomenon, and then also within the gun tubes. And it occurred to me we could potentially do the same thing with stress corrosion cracking in our oil and gas pipelines. But first of all, we have to convince ourselves that the mathematics that Parker came up with are legitimate. So this we go to the Pipeline Research Council of the American Gas Association work from 1974. And if you dig through those symposium notes, you find this quite fantastic micrograph of a cross-section through a failed pipe, which has got some stress corrosion cracking in it. And it is not exactly perfect, but I think you can sort of see that there's a 3-to-1 spacing ratio there. What I've done to just make it a little bit clearer is I've added a few annotations here. So if we look at the left-hand side there, we've got a deep crack, which I'll just say is an arbitrary of 3 units deep. And then approximately that spacing away, a 2H of 3, we have a smaller crack that's about 1/3 of that depth. And then we go another 2H equals 3 away, we find another shorter crack. We keep going a little bit further, and we find the deep crack that ultimately failed this particular pipe. And then as we keep going across the page, across the micrograph, we're seeing more cracks spaced at that 2H equals 3 spacing, and we also see a crack depth of 3 and a crack depth of 1. Now, this is all approximate. You're obviously not going to bet the farm on this happening perfectly every time, but given that it's a natural phenomenon, it seems to be really an interesting coincidence that this is showing such a nice ratio. Now, for those of you that aren't familiar with some of my other work, I've come up with a failure pressure model, which I call the gamma exponent model. In some ways, it's very similar to the original log secant model from about 50 years ago. But in my case, I've done the derivation rather than based on length. I've gone through the entire strip yield model log secant derivation with a focus on depth, and I land on this particular equation. I'm not going to get into the details too much right now, but let's just say that that's the equation that I'm going to be working with. And what I've decided to do is come up with a way that I can modify the crack depths in this equation and account for that spacing ratio. Now there's some fine print. I'm just going to bounce my way through it. If you're interested, please pause the video and take a look. More fine print, all sorts of stuff to think about. These are detailed in some of my other videos. Now, we saw before that when you look at the Tada, Paris, and Irwin work, either the red curve or the green curve, we seem to be bouncing between two different compliance factors. One is 1.03 and one is 0.72. So my question is, how can we fit those correction factors into the model without completely reworking the model? And what I did is I came up with a way where I can modify the crack depth to give an effective value of that 1.03 or the 0.72. So if I just look at the top row here, I say my stress intensity factor is going to be equal to kind of the standard 1.12 times the stress times the square root of pi times the crack depth. But in this case, I'm going to put in an F factor. That's going to be a correction factor that's going to allow me to approximate into the sort of translated stress intensity factor. So if I then make that equal to 1.03 times the stress times the square root of the pi times the crack depth, I can come up with a way to come up with a factor. So if I put in 1.03 there, go through the math, I end up with a correction factor of 0.84. And if I take the alternate value of 0.72, I go through everything, I get a depth correction factor of 0.42. So it's my argument that if we believe in the Tada work and we believe in the Parker work and we believe in the PRCI micrograph that I just showed you and everything packages nicely, after we've gone through an initial crack and shed sequence with our stress corrosion cracks, we should then be alternating between an effective depth of 0.42 and an effective depth of 0.84. Now those two average out at 0.63, so that provides another number for us to play with. Now what I'll do is essentially I'll say that my effective crack depth is equal to that correction factor 0.84 times pi over 4. I'm approximating a semi-ellipse and then multiplying by the maximum crack depth. Now when I go through the whole validation exercise using my new GEM model, I get some pretty interesting results. Here I've got a validation plot using my GEM model. On the y-axis I've got the predicted failure strength. On the x-axis I've got the true failure strength. And then I've got my various data points plotted in the middle. Now what I've done here is the symbols, the triangles, those represent a correction factor of 0.63. So I've just taken the average. And then the error bars you see, those represent the 0.42 correction factor or the 0.84 correction factor. Now, when I plot all of these data points, ideally everything would pretty much lie along that gray diagonal line. Things are not too bad. On the left side of the plot, we have a single service failure, which is non-conservative, which makes me a little bit unhappy. On the right side of the plot, we have 3 data points that are a little bit overly conservative. Those are safe, but a little bit inaccurate. But then in the middle, between the 60% and about 100%, I've got a series of data points that actually straddle the line. And what that means is it gives me confidence that those correction factors are working properly. Now, what I've decided to do going forward is to say to myself, if I'm concerned with service failures, I'm going to use the more conservative value of 0.84, and that's going to get me a little bit closer to the line. I think it's reasonable to assume that if you have a service failure, it's more likely that that's going to happen when your cracks are at the peak of their crack and shed sequence. Whereas if you're doing some hydro tests, like most of these data points are, if you're doing a hydro test either in the lab or you're doing a hydro test in the field, all of the cracks in your pipeline are going to be, I'm going to assume, sort of randomly distributed between the correction factor of 0.42 and the correction factor of 0.84. You don't know where those cracks are in the crack and shed sequence, and so it's reasonable to assume that they'd be fairly much scattered through there. So the way that these data points line up gives me a lot of confidence in the technique. Obviously, I've only got 9 data points, which is not enough to really prove this thing definitively. I'm open to receiving other data, though I found it's quite difficult to find. Now, if I look at the statistics, if I take those hydro test values and I put in a correction factor of 0.63, the average, like I plotted, I have an accuracy for the model of 1.06, and that's based on the mean of the failure ratios, where the failure ratio is defined as the true failure strength divided by the predicted failure strength. So it's a little bit conservative. And the precision there is 0.16, so that's based on just simply the standard deviations of those failure ratios. For my one and only SCC service failure, I use F equals 0.84, and there I've just got simply the accuracy there of 0.85 demonstrates that that particular data point is non-conservative. Now, at this point, I've only got a few data points, so I can't tell whether the model itself is non-conservative or if that just happens to be sort of a natural outlier. And if I had more data, I'd be able to figure that out. If you've enjoyed this video, which I hope you have, if you've made it this far, I do have 2 other series of videos you might be interested in. One is called Pipeline Integrity, Things That Make Me Go, and that's 6 parts. Each part is about 10 or 15 minutes. And that video series is a critique of the NG18 based assessments for both corrosion and cracking. The NG18 equations were developed and they mathematically focus on flaw length rather than flaw depth like the GEM does. So I basically point out the sort of technical and mathematical rationale why the NG18 equations are, I don't think, as good as they could be, and shifting the math around a little bit, like I have with the GEM, is a step in the right direction. I've got a second series called Pipeline Integrity Gamma Exponent Model Validation Parts 1 to 6. And that's where I go through the GEM validation exercise using multiple different flaw types, both axial and circumferential surface cracks. I look at axial SCC, I look at corrosion metal loss, and through-wall cracks for leak rupture boundary analysis. So far, my validation work has been going quite well, and I think that my accuracy and precision are improved over other models available in the industry. Obviously, I'd like to get more and more data to sharpen up some of the statistics, but that's where I am right now. If you'd like to do some reading, I do have some real publications, one through NACE and 2 through ASME. If you're interested in the mathematical derivation of the GEM model that I sort of ran through fairly quickly, look for my ASME Journal of Pressure Vessel Technology paper. It gives you all the mathematics behind what I've done and why I've done it. Essentially, it comes down to the original log secant model was based on a through wall crack, and that's really not the best way to go for a surface breaking flaw. My GEM derivation is essentially a reevaluation of the log secant model, but focusing on depth rather than length. If you've made it this far, thank you very much. I appreciate your time. I hope that some of what I've said here makes sense. I know that working with the Tada plots is a little bit tricky to wrap your head around. I certainly struggled with it at the start, but when I figured out what was going on, I think I've come up with some correction factors that seem to work quite well with my GEM model, at least. And I think that finding the microstructure, the metallography from the original Battelle work from 50 years ago really demonstrates that the Parker approach is worth thinking about. So until next time, thank you very much for your time. Bye.